last time we proved this theorem, which is shown here. Oh, is it visible? Yeah. So the theorem is about a data matrix whose rows are independent of Gaussian vectors, which we denote as xi here. And so we have independence across rows, but each row generally could have a covariance matrix. Here we are assuming that we are trying to estimate the second moment matrix. If the rows are zero mean, then the second moment matrix is also the covariance matrix. Otherwise, it's the main component of the covariance matrix. So as I mentioned, you could see if you have it here somewhere. You can estimate basically the covariance matrix would be the second moment matrix minus this rank 1 matrix, which is based on the mean of the distribution. And the mean can be estimated like that. So you plug in this here, and it's easy to show that this would get you a consistent estimate if you have a consistent estimate at this point. So we focus on the second moment matrix. And last time we proved this result, which is to say that the sample covariance matrix, which can be written like that, so or the sample second moment matrix is the average of xi transpose. This turns out to have this nice deviation. So sigma hat minus sigma in operator norm is bounded by root d over n plus d over n plus delta times the sigma squared, and sigma squared is the bound in the sub-Gaussian norm of each row. So it's notable that this is not a square, but sigma is a squared, and so if you have like a operator norm squared or Frobenius norm squared, this would be sigma to the fourth. And the reason is that this is obtained by multiplication of these guys. So each one has a sub-Gaussian norm sigma. So the product is sub-exponential with its norm sigma squared. So it's worth noting this. And the rest is, let's say if d over n is less than 1, this term is bounded by this guy. And so the root over d over n is the scaling that this error will have. And generally, this can be bounded by the operator norm of sigma, let's say in the Gaussian case at least. So this result gives you a nice deviation bound. And and then we talked about like implications about the sample complexity of estimating the covariance matrix, which is roughly like d over epsilon squared, right? So that's the nice outcome, which is not that obvious. So as I mentioned, there are d squared entries in the matrix, but you don't need d squared, sample size d squared. You only need a sample size d, at, like bigger than d, comparable to d. Okay, and then we talked about the proof. I'm not going to go over it, but the idea was basically use discretization, a form of discretization, plus bounds on like the quantities that appear here. So u transpose this deviation times u, and these turn out to be sub-exponential. And then you put them together. You would get a bound like this. There's this exponential term, which is the cardinality of the epsilon net, and there's this exponentially decaying term, and then you balance the two. So you need to take t to be of the order of root d over n to be able to kill this term. And then there was a little bit of a trick to turn this into the argument here, and then figure out the nice nice form of this bound, which turned out to be like exponential, and then put this back into the probability bound using some sort of a inversion lemma. And so you managed to prove this result. So this was sort of one of the, I would say, highlight of the course. The argument is not that difficult, but the result is interesting and quite sharp, and it just combines a lot of the techniques that we had. So epsilon net ideas using discretization basically for the operator norm, and the sub-exponential bounds for products of sub-Gaussian variables. So make covariance matrices or second moments are like terms are products of sub-Gaussians if each entry is sub-Gaussian or if each row is sub-Gaussian. And you put them together, and then you adjust the like choose the constants, the tail behavior in the tail behavior, and then you get this sort of fairly nice result. So questions about this? Did anyone have any question? Okay, so today I'm gonna just finish the discussion of covariance matrix estimation. We can ask whether we can do better, let's say. So this d over n is still quite large, and if you're in a high dimensional setting, d much bigger than n, the bound would be like of this order, and it's not that useful. You might think that maybe our bound is loose, but the bound is not loose, and you can just estimate the covariance matrix very well, or not at all. The easiest way to see it when so anyone can sort of give some sort of an argument to see what would go wrong if d is much bigger than n in terms of this deviation. So you can think about this, but generally speaking, let's say I have this is covariance matrix, the covariance matrix like identity. If d is much bigger than n, this would be rank deficient, and so one of the eigenvalues would be at least 0. And then the operator norm between the identity matrix and a covariance matrix whose or a matrix, so between the identity matrix and a matrix whose one of the eigenvalues is 0 is going to be bounded below. It's not going to be getting close to 0 in any way. Whether you can show that, for example, this is going to be roughly of this order, or give examples of sigma for which this is of this order, would be interesting in the case where d is bigger than n. But you can justify that at least you can't set it get close to 0, and there are also other results in random matrix theory when d and n both go to infinity. There's the Marchenko-Pastur law. You can take a look, and then there's sort of asymptotic stuff. What happens with the maximum eigenvalue of this asymptotically. So the minimum eigenvalue would be 0. The maximum eigenvalue, this has a limit, and based on that, you can control the deviation, let's say from the identity at least, when this is identity. And you can sort of convince yourself that this bound is quite sharp. So what we can do here is instead make some structural assumptions on the covariance matrix. Okay, and the easiest way to see that this would help is if you work with diagonal matrices. So if you assume that the covariance matrix is diagonal, something like let's say D1, D2, up to D, or D is bad. So say sigma 1, sigma 2, 2 up to sigma DD, and then 0 elsewhere. So we're going to work in this class. So I'm assuming that the covariance or the sample, I'm just going to call it covariance matrix, but it's really the sample, sorry, the second moment matrix. If we assume the covariance matrix is of this form, then I can just, let's say, threshold my estimator, so I can just look at the diagonal entries of this and set everything else to 0. So that makes sense because I know that everything else is 0. So we would look at the, let's say, thresholded sigma hat, which just has sigma hat 1, 1 here, up to sigma hat DD, and then 0 elsewhere. Then you can show that this is not correct. So you can show that T sigma hat minus sigma in operator norm could achieve a bound which is like root log D over N. Okay, so this is one of the exercises I believe I'm going to assign. This suggests that sparsity might help. So if I know the covariance matrix, this is a very sparse covariance matrix. If I know the covariance matrix is quite sparse, then I can achieve, instead of root D over N, I would get root log D over N. Okay, so before we move on, anyone has an idea how to, like, just a quick argument why this would be root log D over N versus root D over N, so that you guys will participate a little bit. So what would be the operator norm of the difference of T sigma hat minus sigma? What will be the operator norm of a diagonal matrix, basically?
It's the largest value.
Largest diagonal value.
Yeah.
What if the diagonals are negative?
I mean, just takes absolute value.
Okay, good. So this would be, in our case, would be maximum sigma hat II minus sigma II, I from 1 to D. So now, why do you think it scales like root log D? Over N?
This is the infinity norm of some sub-Gaussian variables.
Great, it's the infinity norm. They're not sub-Gaussian, they're sub-exponential, but very close, yeah. And so that was the idea. So we did the infinity norm of a sub-Gaussian vector. And so the idea is that these would like have a parameter which like scales like this, and there are D of them, so you'd get root log D times that. Although there's a difference here that, so this would be the size of psi1 norm, basically, something like that. Things are not sub-Gaussian, but sub-exponential, but the same idea goes. So the root log D comes from the union bound. Okay, so instead of taking the supremum over some sort of a so if you go back to the general the definition of the general operator norm, you have to take the maximum over the sphere, and this sphere is d-dimensional, and so this causes like the blow up, like 9 to the d in the union bound, or the size of the epsilon net. Here you have the maximum over just the diagonal entries. So the union bound just needs d, like would have d terms, d times some e to the negative n times like delta squared, or minimum delta squared and delta. Here you would have 9 to the d times that, and so that's the difference. So this was just a quick like hand waving proof of this result. Okay, so it makes sense to people. The sparsity helps. I suppose it makes sense. So diagonal is like the diagonal assumption is too strict. What makes sense is to assume that, let's say, a lot of the entries are 0, but we don't know where they are. So that's the usual sparsity assumption. So you're going to assume that sigma has the sparsity pattern, and the sparsity pattern we're going to represent with this so-called adjacency matrix. So if you think of the locations where sigma ij are non-zero, that would give me a matrix. So for example, if I have a 3x3 matrix, I might have like the diagonal entries are non-zero, and this entry might be non-zero, so I put a 1 here, then the rest is 0. So that's the sparsity pattern, and this is going to give me the adjacency matrix of a graph. So ignoring the self loops, this is like 1, 2, 3. We have like 0 here, which is saying that there's no edge between 1 and 2. So these are basically like the nodes. And so there's an edge between, let's say, 1 and 2. If the entry 1, 2 of this matrix is 1, so there is an edge between 1 and 3. And there's no edge between 2 and 3. Okay. And so that would be the graph. So in general, if you have a covariance matrix, the sparsity patterns can be encoded by this adjacency matrix, or this sort of undirected graph. And the sparsity of the covariance matrix means that the graph is sparse. There's a lot of missing edges from the complete graph. Okay, and so we'll see that we can measure the sparsity of sigma effectively by the operator norm of this adjacency matrix. So one option is to, for example, assume special case is to assume that each row, for example, has S non-zeros. So let's say the L0 norm of each row is bounded by S. Then it's not hard to see. Well, I believe actually we may set the diagonals to 0. I think that's what we're going to do. For I not equal to j, I believe. So if that's the case, then if each row is at most S sparse, then you can show that the operator norm is bounded by S. So each row would have at most S minus 1 entries, or the degree of the graph, the degree of each node, which is the number of neighbors, would be at most S minus 1. Then the operator norm would be at most S minus 1, or bounded by S. And this uses this inequality that the operator norm is controlled by the L infinity operator norm. So this is like the infinity to infinity norm, which is nothing but the maximum, one of them, like maximum, I believe if I've written it correctly, it's the maximum row sum, maximum absolute row sum. But this is a symmetric matrix. L infinity and L in 1 are the same. So either maximum row sum or the maximum column sum is the same. But in general, this would be, anyone remembers the inequality here? So what is the inequality in general between the L infinity and, so this is like the 2-2 operator norm. It's good to remember that this in general is bounded by square root of the infinity to infinity and 1 to 1. This is like the interpolation lemma. I'll talk about this in the notes that I posted. For the symmetric matrices, these two terms are the same. And so you'd get the simple bound that the infinity norm would control. This is not the vector infinity. This is the proper operator infinity norm. So this suggests that this operator is at most S. But this sparsity pattern can encode more like other patterns for which this might be smaller. And we'll say that we can control the sample complexity based on this. Questions? Okay, so if I have a sparsity assumption, what would be a good estimate? Let's say if S is sparse, not S is sparse, but like hard. I have a hard sparsity assumption. Many entries of sigma are 0. What would be a good estimator? So sigma hat is not necessarily a good estimator because it's not using that information. How should we adjust the estimator to use this sparsity assumption? Any guess? Naveen, are you saying something? There's no. Oh.
Can you hear me now?
Yes. Yeah.
Okay, cool. Sorry about that.
Yeah.
I was saying maybe the idea would be to try and solve some kind of like lasso type problem to like induce sparsity.
Okay, so what kind of problem should we solve? That's a good idea. Let's see if I can have. So there's no. So it's not like a regression problem where we have a response and we have covariance. We just have the matrix X, right? X is in n by d. Right, in regression, you also have a response. And then the lasso makes sense. Here we have like this, and then the traditional covariance matrix is something like this. So how do we come up with an optimization problem for which we try to add some sort of a lasso type penalty? So where does this guy come from? One way to drive it is like using the method of moments, right? So this is like the sample average of this population average. So you can say this is the method of moments estimator. But there are also other there's another alternative optimization characterization. So if you have like a Gaussian setup, so suppose I have normal with mean 0 and covariance sigma, IID. Okay, what would be, let's say I can form the, find the MLE, MLE of sigma, right? So how do we do that? So the likelihood, someone help me write the likelihood. So the likelihood would be, you're given, let's say X, would be proportional to what? Would be the PDF of maybe the I from 1 to n. PDF, say xi given sigma, something like that. So what is this PDF? 1 over, or?
It's 1 over the 2 pi to the n times the determinant of sigma.
1/2, right? Okay,
and then times the exponential of negative 1/2 x transpose sigma inverse x if x is 0 mean.
Yes, okay, yeah, we're assuming that that's 0 mean. Yeah, so if you haven't made any mistake, this is correct. So this would be proportional. I'm going to drop the constants, would be 1 over determinant, or n squared, n over 2, and then x negative summation I from 1 to n. There's going to be a 1/2 here. Xi transpose sigma minus 1 xi. Okay. So there's a trick that I can do to get the covariance, sample covariance involved. So I can use the trace trick. Can we like make the sample covariance appear here? Using the trace. I'm going to say that this is equal to its trace, xi transpose sigma inverse xi, because it's a scalar, right? Anyone knows the trace trick?
Can't you just like change the order of the
Great.
terms?
Yes, so that's the trick. You can do cyclic permutations within the trace. It doesn't change. So I'm going to move it that way. So what is the next step in this trick? Why this is useful? So I have xi transpose sigma inverse xi. This is equal to sum I from 1 to n trace sigma minus 1/2 xi transpose, right? What is the final trick?
Use linearity of trace.
Great, okay, so trace is linear, this goes in. That's why we changed the order. So I can put the sum here. And what is this? This is basically n times ahead n, right? So if you like take the log likelihood up to constants, this would be constant plus n over 2 log determinant here, and then negative 1/2, negative n over 2, this n comes out. When you take the log, you get n times times the trace of sigma minus 1/2 sigma n. And you can see from this calculation that sigma hat n is a sufficient statistic, because the likelihood, or the trace of the likelihood, only depends on data through this. So this is a natural sufficient statistic. And indeed, it's actually the estimate, the maximum likelihood estimate. So this is the loss. This loss is interesting. So this, if you look at this loss, it defines a matrix, a loss between two matrices, sigma hat n and sigma inverse. And so the MLE maximizes this. One way to do it is to take the derivative, you differentiate. And I encourage you to try it. Or you could define it as omega. This is like the precision matrix. So this would be the determinant of omega would be negative, or this would be 1 over determinant of omega. So you get the signs flipped, and you can try to estimate the omega. So differentiate with respect to omega or with respect to sigma, whichever you want, and set it equal to 0, and conclude that the MLE is sigma hat n. So the MLE maximizes this. Now, if I have sparsity constraint, I can try to, with sparsity, we can solve a lasso type problem. So I have to minimize the negative of this, which is going to be negative. So I can also divide by n over 2. Let's say I can do the or put the n over 2 there is fine. So n over 2. Let's say trace sigma negative 1/2 sigma n minus log sigma, that's the loss, plus lambda, let's say sigma. This is the L1 vector norm. So this would be summation sigma ij, inj. And so this would be the natural sort of lasso type estimator. And this is called more or less the graphical lasso. Actually, this is not the graphical lasso. The graphical lasso is something else. The graphical lasso would be to put to solve for the omega, which is I believe something like that. If it did not, maybe something like this. My signs might be wrong, but plus lambda. So you would put the sparsity on the inverse covariance matrix, or the precision matrix. And the idea being that if the inverse covariance matrix is sparse, sparsity in the inverse, covariance matrix, then this is a good problem. And the sparsity inverse covariance matrix corresponds to if you call from 200, I mentioned a little bit graphical model connections to this multivariate normal distribution. So this is sometimes called the Gaussian Markov random field, and the zeros of the precision matrix would be the zeros in the graphical representation, or the non-edges. So the non-zeros would be the edges. And so if you do the graphical representation, the sparsity pattern of this determines the graph, not the sparsity pattern of sigma. And it makes sense to assume that omega is sparse if you assume many conditional independencies rather than usual independencies. So, but in any case, so this is one other chapter of the book in graphical models. This is analyzed. This is our natural sparsity in sigma. But we're not going to analyze this. So far, so good. If you're interested, you can do it. What you can do instead is do a very simple. Instead of this loss, I can do like something like sigma hat n minus sigma. This is a very simple loss, replacing this complicated loss. And yeah, you can also drop this. I'm not sure the common formulation. I forgot whether they put it there or not. It doesn't matter because it just changes the scaling of lambda. So you can really scale the loss and it just changes the lambda. And so instead, we can look at this problem. This is a complicated loss, and the solution of this problem is not easy to obtain. You can do it numerically, but not in closed form. Whereas if I replace that loss with this, that would be just a very simple, like there's a closed form solution for this. Because this is separable. So this is like minimizing each coordinate separately. I can do it. Well, actually, there's an issue with, so here this is positive semi-definite. So if I also drop this, it would be easy otherwise. So if I drop the constraint that sigma is positive semi-definite, then I can optimize on constraint over coordinates. Anyone knows the solution of that problem? Argmin here. This would turn out to be a thresholding operator. It's called soft thresholding. So you'd apply it to each entry, basically. This would be T lambda sigma hat ij, where T lambda is the soft thresholding operator. Soft thresholding is something like you would, in negative lambda would be 0 and then gradually sort of increases from 0. Hard thresholding would be something like 0 here. And then equal to the same thing outside. So yeah, how to show this? It would be something like, let me do it as soft thresholding. This is the hard thresholding operator. So this is hard thresholding, this is soft thresholding. So there's a bit of shrinkage here. So in hard thresholding, once you're outside, so T lambda of x is equal to x if norm, like x's or absolute value is bigger than lambda and 0 otherwise. In soft thresholding, things are a little bit different. What would it be? If x is bigger than lambda, basically you would get something like you subtract lambda here, and this would get multiplied by the sine of x, otherwise 0. And the solution of this problem would be soft thresholding. There's a bit of bias introduced basically. Once you like outside the thresholding zone, you shrink the magnitude a little bit, whereas this just produces the right thing. So we're going to study this operation. because things are simple enough. We don't need to introduce this bias. We don't need to really solve this. But similar arguments would hold for this as well. There is also the hard thresholding, I believe, is connected. I don't recall exactly, but you can also put the L0 norm here. And this one also you can sort of solve in closed form, I believe, which would be related to this hard threshold. Okay, so this was a lot of discussion for motivating a very simple estimator. So instead of doing complicated optimization problems, you just threshold every entry. So you can think of this as a form of doing like a basic Lasso type problem, but it's just a trivial loss function because the loss function here is like decomposable or separable, and this is also separable. You just have to solve this problem, argmin. So you have like let's say x hat minus x squared plus lambda x. And the solution of this is just the soft thresholding operator. I'll let you figure this out. Or there might be like 1/2 here. I don't know. There might be something like this that whose solution is. Otherwise, the lambda would change. Okay, sounds good. Did we motivate things enough? So at the end of the day, we will study hard thresholding sigma hat n, which is just thresholding every entry of this guy using this hard thresholding operator. Okay, questions? Okay, so here's the result. So if you have that hard thresholding operator, which we can also compactly write like this, this is applied entry-wise, then the result is something like that. So if xi's are 0 mean from a distribution which is sub-Gaussian, so each entry now is sub-Gaussian with this parameter. Because we're doing thresholding, we need sort of sub-Gaussianity of the entries. And then the covariance matrix is sigma, as though there is dependence within rho, but now every entry of sigma, every entry of the data matrix is assumed to be to have this bound on its sub-Gaussian norm. Then if n is bigger than log d, and if lambda, the thresholding parameter is like that, then we'd have this sort of nice result. This is saying that with high probability, if I look at the hard threshold covariance matrix, the deviation to the operator norm, in operator norm to sigma would be of this size. And again, you can imagine I can take delta to be of the same order as this. This is similar to what we had before. So let's say this would be like sigma squared root log d over n with proper choice of the delta, proper choice of delta. And so this is saying that t lambda sigma hat n minus sigma operator norm would be, with high probability, would be bounded up to constants by lambda a sigma op, or basically sigma squared a sigma op root log d over n. And for example, in the case where we assume that the rows are S sparse, this was its most S. We argued that earlier. And so you get the bound like this. You get that the difference is S root log d over n. So you'd pay this extra price of S here relative to the diagonal case, but it's much better than root d over n, which is what you would get without sparsity and without threshold. Okay, so assuming S is much smaller than D, this is a consistency result. And there's another like exercise we probably assign. I'd probably assign that says that this could be in cases smaller than S. So for example, if you have so if you have a clique, so if you have a graph, for example, where there is a clique of degree S minus 1. So every node basically, clique means every node is connected to every other node, and there are, let's say, S minus 1 other node. So the clique is of size S. So the degree of each node in this clique would be S minus 1. Then you can show that this has to, the operator has to at least be S minus 1. So this can't be improved if you just assume that the graph has the neighbors are like the number of neighbors bounded by S. If there's a clique of size S, then this operator would be as big as S. However, there are cases, for example, this hub and spoke structure, that there's one node like connected to like S of the other nodes. That's the extreme, the other extreme. So this you can show that the operator node would be bounded by something that scales like root S. So in that case, this would be of the order root S, and then so the S goes inside the bound, and this would be a much better scaling. Okay, so this is sort of adaptive. The way that this bounded structure is adapted to the level of sparsity. So for a specific sigma, it could be smaller, or it could be as large as S, as small as root S, and I believe probably it could be 0, like it could be just this thing. But the scaling is roughly, if you want S sparsity, if there is some sort of S connections, probably this is the smallest that it can get. At least that's my guess. You're welcome to show or disprove. Okay, so the result is clear. So how do we prove something like this? Maybe let me ask you guys, see if we can prove it together. What do you think we should do? Should we use discretization or that kind of argument? So I'm going to help you. Discretization, that argument is not going to be very useful because this operator is pointwise, and we're going to run into issues with controlling pointwise deviation. What we're going to sort of try is to relate this to the infinity vector norm, because this is a pointwise operator. Then the pointwise infinity norm would be interesting. And there's a little bit of a technical setup that we need. So what we are going to do is that we're gonna use this result, which is another exercise that you're going to do. If A is bigger than B, bigger than 0 pointwise or element-wise, then you'd prove that the operator norm of A is bounded by the operator norm of B. And the next result is that if I have a matrix and I put the absolute value around each entry, then the operator norm of C would be bounded by the operator norm of this new matrix. So these are not obvious results because like the operator norm is not like naturally pointwise operation, but it turns out that these inequalities hold and they're useful for controlling element-wise sort of properties. I mean, what happens if you do like element-wise operation to the operator norm? So what we're going to do is prove a result like this. So if sigma hat n minus sigma is if you have a pointwise or vectorized L infinity bound, so this is just sigma hat n minus sigma L infinity, which is the maximum over ij, sigma hat ij minus sigma ij. If you have a vectorized bound on the infinity norm, then we're going to prove that this operator norm is controlled by this. And then we have some idea what this is. Okay. Let's try first try to prove this. Let's see if we can prove this. Prove it here. So we have sigma at n minus sigma. The entries are, I know that they're between lambda. Then I want to show that the operator norm of this thresholded matrix, sigma hat n minus sigma, is bounded by 2 lambda a sigma of norm. So we're going to do this. So if there are two cases. So if sigma hat I is 0, and if it's non-zero. So if sigma hat I is 0, so what would be the say T lambda? See, I want to do, right, I want to do the pointwise. What did I, right, so let's do, sorry. What would be this absolute value? T lambda sigma hat ij minus sigma ij. We're going to try to control this pointwise. So instead of the operator, we're going to do a pointwise bound on it. So if we can show, for example, that okay, this is not gonna, so what I'm gonna do is, let me do this first. What I would like to do is show that this is T lambda sigma hat n minus sigma infinity norm is bounded by, oh, sorry, not infinity. This is bounded by this guy. This in absolute value is bounded by 2 lambda a sigma. And everything here, both this and this, are element-wise. Okay, so we're going to prove an element-wise inequality like that. And then if that's the case, then we're going to use these two arguments. So this is bigger than this. So what I would get from this is that the operator norm of T lambda sigma hat n minus sigma, this pointwise matrix, this operator norm is bounded by, because this is also bigger than 0 pointwise, bounded by the operator norm of this, right? And this is just 2 lambda operator norm of that. And then by part B, this is also going to be bigger than the operator norm of T lambda sigma hat n minus sigma. Okay, so that's the idea. So we're going to prove an element. So this implies this element-wise inequality. And then if you have that element-wise inequality, we get the bound that we want. We get this bound on the operator norm. And so this is what we want. And then later on, we'll show that this lambda, it's easy to control this because this is an element-wise bound on something that we know. And then we'll show that lambda has to scale like that. Okay, so this is so far clear. So now I'm going to prove this. Okay, and in order to prove this, because this is just an element-wise inequality, so if sigma ij is 0, then a sigma ij by definition is 0. So this inequality turns into this is less than or equal to 0. Okay, and if so, we need to show this if sigma hat ij is bigger than 0 or non-zero, then this guy is going to be 1. So then the inequality is equivalent to T lambda sigma hat ij minus sigma ij is less than or equal to lambda. And in fact, because here this is also 0, this is just equivalent to T lambda sigma hat ij being 0, and this is just this. So I need to verify these two cases. Okay, so now why these two are true. So if sigma ij is 0, why would I get that inequality? The condition is that we also know this. Okay, given that, why these cases hold? Anyone?
If sigma ij is 0, then sigma hat ij is at most lambda, and the hard thresholding operator would turn that lambda into 0.
Okay, great. So this implies sigma hat and ij. I'm just going to drop n maybe. Okay, this is just the absolute value is less than lambda because this is pointwise. This is saying that the maximum over each entry is bounded by lambda. So sigma ij is 0, so I get this, and the hard thresholding as you pointed out, if you remember what it does. So anything in this interval between negative lambda and lambda maps to 0. So because that's the case, then indeed this is the case. So we're going to get 0. So how about this one? So in this case, we still have this is still true. No, this is not true. Okay. Sigma ij is non-zero. So why this is true? this is not true. Maybe that's why you don't say it, because the should be 2 lambda. And there's a 2 lambda here. Now, why this one is true?
Can you add and subtract sigma hat ij and use the triangle inequality?
Great, yes. So that's what exactly what we're going to do. So this is going to be t. So you have t lambda sigma hat ij minus sigma ij is bounded by t lambda sigma hat ij minus sigma hat ij plus by triangle inequality sigma hat ij minus sigma ij. So this is bounded by lambda by assumption. And this is like the error in hard thresholding operator. So if you have like x, in general, this is like a scalar, this would behave like, so if you imagine there's the x here, that's the graph for the function x. This is t of x. And so the difference would be 0 outside this interval, right? So if I look at the t lambda of x minus x, it's going to be 0 here. And in this interval, it's just going to be this, right? Right, and so the absolute value is just going to be, you can see the absolute value here is going to be bounded by lambda. This is just going to be like this. T lambda x minus x absolute value. If you plot this function, it would be like that. And so this is going to be always bounded by lambda. So this is always bounded by lambda. So this whole thing is bounded by 2 lambda. Okay, so if you do a plot, you can see the error of soft threshold, like hard thresholding, is at most lambda. Okay, so we proved this inequality that we wanted by considering 2 cases, and this is a pointwise inequality. It translates to an operator norm bound via these 2. So the argument is not difficult, but it's quite, I would say, clever. Whoever did this first, probably Bickel and Levina, they used or they use similar ideas, not exactly this. These 2 are not that obvious, sort of obvious way of treating operator norm. Or maybe someone else like this is do someone else. Let me know if I made a mistake. I think they use this bound, but to control that, maybe control this by the maximum row absolute sum. I'm not sure exactly this is the result that they have, but this is a very clever argument, I would say. The reason is that this guy is small because it's a maximum infinity norm, like the element-wise infinity norm. You could do what? You could control this easily. Okay, so if this is controlled, then this bound holds, and it can choose lambda sufficiently large such that this holds with high probability. Okay, and exactly how large I need to take lambda for this bound to hold, this is exactly the size. Okay, so this is saying the probability that this minus this bigger than lambda is bounded by, let's say, I don't know, 8 to the e to the whatever there is there, min delta and delta squared, if lambda is taken to be this guy. Okay, so if I take lambda to be this, then I have this bound. And this is a bound that you can establish. I believe I'll put it as a homework exercise. So the constants are not important, but each entry is sub-exponential, and this is like maximum over d squared entries, or roughly of this d squared size. And so you would get a union bound plus the sub-exponential tail bounds would give you this. And so the probabilistic part of the argument is this, that the L-infinity norm of this deviation basically scales like that. And then the clever part is to relate this element phi's to the operator norm. And so you'd get a very interesting result like this. Okay, questions? Comments? Okay, one last thing is, well, actually I've proved this here. I would like to let you do this yourself. Maybe I shouldn't include this here. So the idea is, again, simple, as I mentioned. So you'd control the like each coordinate is sub-exponential, the sum of a bunch of sub-exponential, average of sub-exponential variables. So you'd have a tail bound for them. And then there's the union bound, which is like that. And then you do a little bit of a trick to get, you can use that sort of, the techniques that we already know to sort of adjust t such that you get the result. Yeah, I'll let you do this yourself. Unfortunately, I have it here. I can't assign it as a homework problem, but I should have assigned it as a homework problem. Maybe I'll assign it still, so that people that come to lecture know where to look if they had trouble. But try to prove this yourself. It's a very good exercise. So the last thing I maybe very quickly mention is that for completely dense sigma, this bound is poor, because that would be 1 transpose, and this would be D. And so we're back in the business, but this is actually much larger. So you would get D here, and then you're also paying an extra price of root log D, which you could have avoided by just using the covariance matrix itself. Sorry, yeah, sample covariance matrix. So what if we have a mild sparsity constraint? So if you have a row sparsity assumption, but the rows are LQ sparse, as we've seen. So the rows are the LQ sort of norm square, like to the power Q, is bounded by RQ. I think this is what the result of Bickel and Levina. There's like a famous paper that did this. Under this assumption, you would get a result like this. So first, you show that if lambda is such that the operator norm of sigma hat minus, or this shouldn't be operator norm, I believe this should be. I think this is probably this infinity. If this is less than lambda over 2, then the operator norm will be controlled by that. This is like replacing the this lemma. So this implies something like that, but now the LQ sparsity appears here. So you get something like this. And then lambda scales as before. So you would get 1 with high probability of this order. And so if you choose lambda to be like sigma squared root log d over n, what you would get is, ignoring sigma squared, a bound which works like that. So log d over n to the 1 minus q over 2. And so you still have like dependence logarithmically in D, and this is, if I recall, more or less optimal. So the power is also correct, if I recall correctly. And so this is a very nice result. This is saying that, so the operation is the same. So you're still doing thresholding. You're doing thresholding at the same level. But the underlying matrix is not necessarily as sparse. Just every entry could be non-zero. But if you look at every row, and if sum the LQ, like form the LQ norm would be bounded. Although the size of the matrix could grow, this LQ norm is not going to blow up. It's bounded by constant, still quite sparse in that sense. Then you have this very nice result that this works like that. You're out of time. There is a, I don't know if I want to do the proof or not. We'll see it next time. The only thing to show is basically this inequality, okay? And this inequality, I could have assigned it as a homework problem actually. There's a simple version, which is you can do it for a vector, and then you can imagine what it would look like for a matrix. So this is just the properties of the hard thresholding and the trick involving looking at the subset of entries that are above the threshold. Remember this trick we used or in your homework problems to deal with the LQ while, and the same idea appears here. So you control this L1 by this trade-off between the size of that set and the L1 or of the complement of the set, and so on. So you either come back next time and talk about this, or I'll let you go over this. But what we're going to do next is I'm going to post like a poll and see what you guys think. I've covered most of the things that I wanted. Now there's one extra topic probably that we can handle, and that would be either sparse PCA or PCA, maybe not sparse PCA, or like functional regression. So I'll try to post a poll and see which one you guys like better, and also helps if I understand whether one of you guys want to talk about these things. Or if you decide to talk about that, maybe you can like talk about some other aspects of it. We're not going to be able to cover everything, so there's still room. But I'm going to post a poll, and you guys be sure to like sign up for the projects. Okay, sounds good. Questions, comments? Okay.